Welcome all of you. Continuing with the solar thermal part, earlier we had seen different types of collectors, how they are classified, what are their performance characteristics, mainly the heat gain and the efficiency part. Did some numericals also. So in today's lecture, we will cover the concept of concentrated solar power and the concentrated solar power plant components. We'll look at some case studies from the world as well as from India and see how they compare in terms of area requirement, land like cost requirement, cost and efficiency, those things. So, solar thermal power plant, it's also called as CSP, concentrated solar power, a renewable energy or a solar powered plant that converts solar radiation into thermal energy, and this thermal energy is subsequently converted to electrical energy through a thermodynamic power cycle. Often it is a Rankine cycle or a steam cycle, because like if you remember the typical power plant, what do we have is a boiler where we put water, and this boiler generates steam, and then this steam is going to the turbine. Turbine is connected to the generator which generates electricity, and after the steam is condensed in the condenser, this condensed water is pumped back to the boiler. We can have a pump here. Okay, so this cycle keeps on repeating, but where is the requirement of solar thermal here? Had it been a coal powered plant, we will need heat here in the boiler, and if this heat is coming from coal, it will be coal fired power plant. If this heat is coming from solar thermal, then it is a solar thermal power plant. So, it is not something different, it is similar to conventional fossil fuel based power plants which operates on like the steam cycle. The only part here different is the source of heat that is fed to the boiler. So, this heat is coming in this case from concentrated solar power. Okay. So, basically solar radiation goes to the thermal energy, this is transferred to the mechanical energy in the turbine, and then generator generates electricity. So, often because we need high temperature steam to generate power, so concentrated solar power should make use of the concentrating type of collectors, mainly mirrors or lenses or heliostat field, which is able to concentrate solar radiation onto a receiver, which will produce very high temperature heat, and this high temperature heat, like more than say 500 degrees Celsius, can be used to generate steam, which can drive the turbine or which can drive a heat engine which is connected to the generator and generates electricity. So, there are two ways. One is solar heat is converted to the steam, then it is used for rotating turbine and generator generates electricity, or it can be used to drive the heat engine, mechanical shaft power which generates electricity. Okay. Both are the approaches by which concentrated solar power can generate power. So, typical concentrated solar power plant will look like something like this. Because we want high temperature, so we would go for concentrating type of collectors. It can be either parabolic dish or it can be heliostat with solar tower or a central receiver. So, these parts which I explained earlier, like the steam generator or a boiler, then a turbine, generator, and then the power lines, and condenser from where water is again going back into the steam generator. And this part, this is the solar thermal part, which is actually capturing solar radiation and transferring heat to the heat transfer fluid. It is a heat transfer fluid. In this case, if it is a steam generator, it can be water. So, it is the water which goes through the receiver, gets heated and then comes back to the steam generator. But between receiver and steam generator, you are seeing these two tanks. What are these? Those are thermal energy storage tanks, because if we rely on solar radiation for generating power or absorbing heat, at night time we won't be having sun. So how would these plants work? So for such, like if you have to run the plant continuously, we will need thermal energy storage tanks, so that hot water coming from this, or a hot thermal fluid which is coming from the receiver, can be stored in these huge tanks, and they are very expensive part of the entire solar thermal plant. So it gives us the flexibility to run the power plant even in the absence of sun. So this, the number of hours for which we can store the solar thermal energy is varies. So it can vary from 8 to 15 hours of storage, depending on what is the material that we are using to store solar thermal energy, right. So this is a typical real world, I think one of the world's first big solar thermal power plant of 582 megawatt in Morocco, and you can see it's a heliostat based plant having a solar tower, and on the top it is a receiver, and so huge. We'll look at this plant details in the case study, but yeah, this is a typical concentrated solar power plant. And the major components, if you look from the solar thermal side, they are solar field and collector mirror system, basically the collectors and the absorber and receivers. Then heat transfer fluid system. So it involves the heat transfer fluid as well as the piping and storage equipment which are used to either hold this or transfer this fluid. It will need the pumping, it will need the pumps. Then heat exchanger, mainly the steam generator or the boiler, where heat transfer would take place from a heat transfer fluid to the working fluid. Okay. Thermal energy storage, like TES tanks which I had shown earlier, okay, to be able to run the plant or generate power in the absence of sun also for a certain amount of time. And then there will be the control system managing all these collectors, mirrors, heat transfer fluid and the flows of fluid. But in addition, now these are the components which are related with solar thermal, but this actual solar thermal power plants will have other elements also that represent standard technology for generating electricity, and they will include boilers, steam turbine, steam generator, condensers, cooling towers, pumps and auxiliary systems, because this part represents solar thermal part and these parts would represent the actual traditional power plant which are steam based. Okay. So those are the components of concentrated solar power plant. Let's take one small numerical to see whether we have understood the concept of concentrated solar power. Let's say we have one 10 megawatt electric output parabolic trough plant, and it operates with a aperture area of 50,000 meter square and direct radiance of 850, that is IB. So if optical efficiency is 75% and power block or the thermal efficiency is, so it's 35% and generator efficiency is typically 95%. Okay. So we have three equipments here and three of them have their different efficiency. The plant uses a thermal oil as a heat transfer fluid whose CP is known to us, and it's heated from 290 to 390. Okay. So calculate the thermal energy storage, that is capacity for 6 hours of full load operation and a total mass of molten salt. So basically the heat transfer fluid here is molten salt for TES, thermal energy storage system. The working liquid or the working fluid in the power plant can be thermal oil, because it's a thermal oil which has to be heated from 290 to 390, and to be able to heat thermal oil from 290 to 390, we will need a heat transfer fluid at much higher temperature than 390. So molten salt can serve that purpose, and it has a CP of 1.5. So let's see how do we calculate. So we know the equation of useful energy gain as well as the efficiency. So solar energy captured by the collector field it will depend on what? It will depend on the incident radiation 850 and aperture area, that is 50,000. So, Q is I into A into the optical losses, so optical efficiency, that is the solar energy captured by the collector field. So, you substitute the values 50,000, 850 and 0.75 and we get 31.8 megawatt thermal, because we are talking about solar energy captured. Okay. Now, the second part is how much is electricity, how much electricity is generated. So, for that we will have to account for both thermal efficiency and the generator efficiency, because after it is captured, a part of it is going to heat the working fluid and then it is generating the electricity. So, energy captured upon thermal efficiency into generator efficiency. So, it is 35 and 0.95. So, the value is 10.6 megawatt electric. So, that is the electricity generated. Now, the third part what we need to calculate is the how much thermal energy storage capacity is required if we have to like design it for 6 hours, and what would be the mass of molten salt. So, thermal energy storage capacity will depend on the heat captured into how many hours. So, we need it for 6 hours. So, 31 megawatt thermal into 6 hours, it is 191 megawatt hour thermal. Okay, because this was in megawatt and this is in hours. So, that is the energy storage capacity that we need. Now, for mass of molten salt, you can calculate by Q equal to mCp dt. So, that is the energy storage capacity, and mass of salt would be energy storage capacity upon Cp of salt into change in temperature. Change in temperature is 100, because we had to heat oil from 290 to 390, right. So, because Cp is going to be in kilojoule per kg Kelvin, we need this QTH in kilojoule. So, if we convert this megawatt hour into kilojoule, we need multiplied by 3600, and megawatt to kilowatt we multiplied by 1000. This is the value in kilojoule. If we substitute it here, Cp 1.5 delta T 100, we can get the mass of salt in kg, or in tons it is coming out to be 4590. So, that much molten salt we would be requiring for a 6 hour storage capacity for a 10 megawatt solar thermal power plant. So, we can make a guess of like how big of a thermal energy storage tank would be required to hold such a big amount of molten salt. So, that is why the thermal energy storage systems, they cost significantly higher. Let us look at salient features of CSP plant. So, concentrated solar thermal power plant, they have 24/7 dispatchability. It can be operated for 24/7 if we have the proper storage system in it, because solar thermal actually it has inherent thermal storage, and fluids like molten salt can store the energy for 10 to 15 hours easily. So, it can provide power through the night. So, unlike solar PV, which do not have inherent thermal storage, we have to rely on the batteries to store solar PV power, but for solar thermal it has the inherent thermal storage. So, grid stability, because it makes use of traditional like spinning turbines, they provide this mechanical inertia or momentum and frequency response, which are critical for maintaining the grid health and stability, and it also helps to avoid blackouts. Again, a feature which solar PV panels lack, but solar thermal plants will have it. Industrial heat, it can achieve temperatures up to 565 degrees Celsius and higher, which is again a governing limit for molten salt, and this can be ideal for hydrogen or heavy industry, because above these temperatures like say 570 or 590, the salt starts to break down. So, at these temperatures molten salt works fine, and then they can provide heat or their fluid properties are maintained. Hybrid potential, instead of competing with PV, they can be actually integrated or paired with PV, and then solar PVT technology can give us lowest cost 24-hour solar power. So those are the silent features of CSP plant, but then there are certain critical challenges also regarding mainly the land, efficiency, cost. So high cost because of huge land area that is required for installing this heliostat, solar tower or the parabolic dishes. There is a significant capital cost compared to standard solar PV, which occupies very less land and are less expensive. Water usage, we need water for cooling tower, and often what happens, solar thermal power plants would be installed in the dry, arid, desert area where we have good sunlight, but then those areas will have very scarce or less amount of water. So that thing we have to optimize, and sometimes when we end up having plants in the desert area, the water pipelines, they need to be very long, and then water usage is a concern in the solar thermal power plant. Complexity, if we have to set up a plant beyond say 10 megawatt or 50 megawatt, a big size capacity plant, they will require thousands of moving mirrors, heliostats or parabolic dishes, and when we have so many number of equipment placed which needs to be controlled to move around its axis, whether it's a single axis, whether it's a double axis, there is a high possibility of frequent maintenance and repair issues. So they need high maintenance. Weather resilience, again, to maximize solar radiation capture and generate high temperature heat, it needs clear skies, and in case of hazy or cloudy weather where most of the radiation would be diffuse type and not beam type or direct radiation type, there the capacity of these power plants which are already running at low efficiency will drop. So there is a huge reliance on weather also. So these are certain challenges associated with concentrated solar thermal power plant. Now if you have to compare the plants in the world and in India, we have taken here 3 plants. One is the Noor complex in Morocco, Miss Godavari in Rajasthan, and another one is also in Rajasthan. India one, it's Abu Road. So these 3 plants are of 3 different capacities, 3 different technology. So let's see how they compare on the basis of land area, cost and thermal storage. Okay. So capacity for Morocco is 582, it's a huge plant. Godavari was 50 and India one is 1 megawatt. Okay. And the technology used here was trough and tower. So parabolic trough and solar tower. So combined it is producing this much. Godavari, it's a parabolic trough, and India one, it's a parabolic dishes. So the area where these 3 plants are located varies from 7,000 acres to 300 to 35 acres. And total cost also varies, 83,000 crore, 880 crore. So you can see there is a like direct relation of like say 100 times, 1000 times, 100 times, and then almost 10 times of this, 20 times of this. Okay. And capacity is again 50 times, and here it's like 10 times more. Thermal storage, that's Nuru plant, it has a molten salt based thermal storage for 3 to 7 hours. Godavari plant uses direct steam, they do not have any storage, and India one has cast iron blocks which can store heat for 16 hours. So cast iron blocks, they actually store they are a form of sensible heat storage, and it depends on the physical mass of the iron to soak up the heat without changing its state. Okay, and these iron blocks are also insulated from outside so that there is no heat loss, and the fluid moving into that iron block can get heated. The primary use was for grids because of the high capacity, and this 1 megawatt was mainly for cooking and captive power. So why Noor complex has such a high cost and such high area requirement? Because if we do the land per megawatt or the cost per megawatt, here let's see, it's 35 acre per megawatt. So accordingly 50 megawatt, we just have to multiply it by 50, but here it's say like 10. So area requirement reduced when the capacity increased 50 times, area did not increase 50 times. But then again, reason can be technology is different. Parabolic dishes, they need high, like large area. But if you look at the cost, is for 1 megawatt is 80 crore. So for 50 megawatt is 800 crore. So it's 50 times, but cost has increased only 10 times. So there we can see the scale of economy factor. But here, when we go from 50 to 500, the cost is not going to 8,000, but it's rising by 10 to the power 2. So why such a huge cost jump between these two type of plants when both are operating on trough? Okay, some part is coming by solar tower also in Noor complex. So the reason for this is, the first reason is the technology is different. Second, this plant works 24/7 and it has a molten salt based storage. Okay, so Noor plant designed for 24/7, it has a huge molten salt storage which occupies or which contributes to 40% of capex, and Godavari plant do not have any storage system. So that's why the cost is significantly higher. Also, the plant in Morocco, it is built in remote desert and it requires huge auxiliary infrastructure, like for example 250-meter long tower and almost 10-kilometer long water pipeline, and that's the reason why cost for Noor complex is significantly higher than the other two plants. But if you look at the area, like India one, it has 35 acre per megawatt and this has only 350 acre for 50 megawatt. Why such small area? This is because the parabolic trough needs much smaller area than the parabolic dishes, which needs to be kept separately. So dish based technology need more space, and that's why the area and cost will depend on the choice of technology as well as the type of thermal energy storage systems that we have in the CSP plants. So hope that clarifies the difference between different types of plants. Let's look at one case study in detail, like India 1 solar thermal power plant, because this was India's one of the first, what we say, commercial level solar thermal plant, established in 2017 at Abu Road. It's in Rajasthan. It's also hill station and famous for Dilwara temple and Brahma Kumaris. So it's a Brahma Kumaris and WRST, it is World Renewal Spiritual Trust, who developed this plant, taking initiative, and then there were other partners who funded this initiative like GIZ, the Ministry of Germany and MNRE. And this plant of 1 megawatt, okay, it is able to produce electricity and steam. So it's actually a co-generation plant. It generates power as well as steam for the Brahma Kumaris campus, which has around 25,000 population. If you look at, so these are the parabolic dish which you can see. This is on the front side which is facing the sun, and these are on the back side where you can see the tracking mechanisms where these can be moved along with the direction of the sun so that it maximizes this solar radiation capture. Now in this dish based, you can see there are tiny receivers in front of each of the parabolic dish. So there are 770 such parabolic dishes, and each dish is having the area of 60 meters square. So you can imagine like how much is the 60 meters square. So it's a, even if I assume it to be a square for easy reference, so it will be 8 meters. So 8 by 8 meters square. So 8 meter is a huge surface which needs to be mounted on this stand. That's why, because of that significantly huge surface, you need a strong and sturdy support. So a lot of metal and engineering has gone into providing or installing and supporting these close to 800 parabolic dishes, and these need to be having sufficient spacing in between so that they are able to move along with the position of the sun. Okay, so that's why this needs huge area, that's also around 35 acres, which we saw in the previous slide, and 1 megawatt is the output. It's a cogeneration based plant, generates energy, and it has a robust static cavity receiver which is able to produce superheated steam at much higher temperature, up to 450 and 42 bar. And thermal energy storage is there for night operation and for steam generation at night, and it has a networked fully automated dual axis tracking system. So this thermal energy storage is basically the cast iron blocks which we had discussed earlier. Now, since it was one of a kind India one like solar thermal power plant, the main objective was not only generating power and steam, but also provide having training and societal impact by conducting like say capacity building and skill development trainings. So it was designed for capacity building equally as it was for power. So far in terms of skills, more than 250 local workers have been trained in the high precision welding and dish assembly, because all those more than 90% of the components of the plant were indigenous and they were fabricated in India only, locally. So local workers were involved in and they were taught how to do welding, how to assemble the dish components. Employment, it provided jobs to 300 tribal community members during construction. Okay, and in capacity building, it trained more than 350 engineers so far by hands-on training through solar thermal workshops, and it has also set up a concentrated solar thermal awareness center in Rajasthan, which is training more than 500 officials and entrepreneurs so far. And public outreach, annually almost 1 million visitors are there who visit this center and get educated on the solar thermal or the renewable energy. So that's a huge training and social impact this plant has. The main reason being because it's localized technology and it is run and operated by a non-profit communities. The investment come from the public and private sector along with ministries from both the countries like India and Germany, but the initiative was taken by a non-profit organization and now it is operating and maintained by the non-profit communities, developing employment for the local region, providing heat and power and steam for the local consumption. So it has worked as a very good model for power generation as well as for capacity building, having a huge training and social impact. So I think that was all. To summarize, what we covered in today's lecture was concentrated solar power plant. So it's actually summary, and we saw different components of solar thermal power plant. There are some components which are specifically for solar thermal side, but then there are other traditional power plant components which are mandatory. That is, those are also the parts of CSP. In terms of comparison, we saw a plant in Morocco and 2 plants in India, and we compared how different technology or different types of collectors can have different area requirement, different efficiencies and result up into different cost. And in the cost, it's the thermal energy storage system with heat transfer fluid which plays a critical role. Like molten salts, it will be going to much higher temperature than 560, and that increases the cost tremendously, costing up to 40% of the capital cost. And then we looked at one of the case studies from India which had a lot of training and social impact, as well as which generated power and steam for a community of 25,000 people in Rajasthan. It is shown that public private non-profit partnership can end up having a successful renewable energy based case study. So with that, we'll stop here and thank you so much.